All right, so in this video, I'm going to go over how to draw a Lewis dot diagram and talk about the valence shell electron pair repulsion theory, which is pretty self-explanatory, actually. I think we make it more complicated than we need to. If you've got two pairs of electrons, because we know that electrons travel in pairs, and they're relatively near each other in 3D space, they're going to repel because they both have negative charges. So this is the theory of how those negative repulsions affect the shape of a molecule. And then in the next video, I'll talk more about the importance of the shape of a molecule. This is just going to set you up to figure out how to determine the shape of a molecule. So the first thing you need to be given is really a molecule. I'm going to start with CH4, right, methane. It's a pretty typical one and it has a pretty important shape. So the first step is going to be to really make an educated guess about the geometry and the arrangement of these atoms. So the world kind of prefers symmetry when it comes to molecular shape. And carbon is a unique atom in that it's very inclined to form 4 bonds. So I'm going to go ahead and guess, right, make an educated guess that my arrangement is going to be something like this. Now, mind you, if you've done Lewis dot diagrams before or know about bonding, you know hydrogen can only substantiate 1 bond. So hydrogen has to be on the outside of this molecule, otherwise it's just not going to work. So the second step is you want to count your total valence electrons. You can do this using a periodic table, or at this point you might actually have some of them memorized. We have 4 hydrogens in this molecule and 1 carbon in this molecule. Every hydrogen has 1 electron. Every carbon has 6 electrons. That gives me a total of 6 and 4, which is an overall total of 10 electrons. So the next step is going to be to count total valence electrons in the molecule. Notice valence, not total electrons, but total valence electrons. I have 4 hydrogens, each of which has 1 valence electrons, 1 carbon, which has 4 valence electrons, 6 total, but 4 valence. And again, VSEPR, valence shell electron pair. So that's going to give me a total of 8 electrons to work with. Then from there, you're going to create your bonds in the molecule, and we're going to represent that just with a straight line. And each of those straight lines is 2 electrons. So in this case, I've used up 8 electrons bonding my atoms together, which leaves me with a total of 0 valence electrons. So from there, you just need to check that every atom has their stable octet, or in this case, we're working with hydrogen, so 2, and that you've used up all the electrons that you have to use. So carbon here has 2, 4, 6, 8. Each hydrogen has 2, 4, 6, 8. My molecule is good. So then from there, we have to figure out, now we have the Lewis dot diagram, how do we relate that to its molecular shape? Last year I taught it this way, and I'm going to continue to teach it that way this year with the ABN formula. A is your central atom, which in this case is carbon. B is your bonded atoms. I have 1, 2, 3, 4 bonded atoms. N is your non-bonded lone electron pairs. There are none in this case, so I actually don't need that. So AB4 is my generic formula, if you will, for CH4. Using a reference sheet or your brain, eventually it needs to be your brain, you're going to look at something that has 4 attached atoms to the central atom, and in this case that's the tetrahedral shape, which has a bond angle of 109 degrees. So unlike in our drawing here, where our bond angles are shown as 90 degrees, in reality, if I would take this and I would blow it up into 3D space, I would have 2 atoms, this hydrogen and this hydrogen, coming out of the screen at me, and this hydrogen pushing back into the screen, which actually makes my bond angle 109 degrees. And remember, that's because electrons do not like to be near one another. So if I were at 90, I'd have this hydrogen and this hydrogen 90 degrees from each other, but this hydrogen and this hydrogen 180 degrees from each other. And there's no scientific rationale for that discrepancy. An electron is an electron and they don't like to be near one another. So why could these be closer together than these? And the answer is they couldn't, which is why it's a tetrahedral shape and you have 109 degrees between each of the bonds. All right, I want to do one more example with you just to show you another example. We're going to do carbon dioxide. It's a good one. It's around in our environment a lot. You create it on a daily basis. So again, step one, predict where these atoms are going to go. In the interest of symmetry, I'm going to place them like that. Second step, count valence electrons. We've got 1 carbon, 2 oxygens. Each carbon has 4 valence electrons. Each oxygen has 6. That gives me a total of 16 electrons to work with. So from there, I'm going to place a bond connecting all of my atoms. That uses up 4. Now this is the step that wasn't necessary in the tetrahedral carbon. You're going to fill up your outside elements first with these extra electrons. So I'm going to give 6 electrons to each of my oxygens because that gives them their stable octet. And that uses up my 12. So now I'm done, except hopefully you're screaming at me that I'm not done because I have not checked that every single atom in the molecule has its stable 8 satisfied. And in this case, it's glaringly obvious to me, perhaps not to you yet, that carbon's stable octet is not satisfied. It only has 2 4 electrons. So now we need to consider whether multiple bonds will help us achieve a stable octet for more of our atoms. So I'm going to take these electrons here and place them in a double bond. So again, I haven't changed the total number of electrons, right? I'm not adding electrons to the molecule. I'm just shifting them around. And I'm going to do the same thing here. Now this oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Now, to be the best representation and focusing on the fact that electrons repel one another, I would draw these electrons on the corners so that they're as far away as possible. And there's going to be my best drawn Lewis dot diagram for carbon dioxide. Now to figure out its molecular geometry, my central atom is carbon. I have 2 oxygens bonded to it. Remember, it's total number of things bonded to it, not total number of bonds bonded to it. And on the carbon itself, again, there are no lone pairs, so I don't even need to write it. If I come to this chart, or the one that you have from last class, AB2 is going to have this shape here, right? My central atom E is my carbon, and my X's are my oxygen. I hope you found this helpful, and I'll see you in class.